Okay, good evening. Last video, we discussed the doubly reinforced USD method. We have the ultimate moment 1 and the ultimate moment 2. We also discussed the 3 failure condition. And we discussed also the specification as well as the theoretical method of determining the section is tension failure or compression failure. And tonight we have the sample problem, USD ultimate stress design problem. We have given here moment dead load 45 kilonewton meter, moment live load 250 kilonewton meter, A prime C 21 megapascal, Fy 276.0 megapascal, and the required is to check the given section. This is the section to check using USD method. So this is our section to check. When we say to check the section, meaning we are going to find out if the moment capacity of this section is either less than or equal or greater than the ultimate moment applied. So that we will going to find out. If the ultimate moment capacity greater than or equal to the ultimate moment applied, the section is safe or adequate. Before we're going to check that, we have to check first the section for failure condition, this one. And we have two ways to check it, by specification and the alternate or the theoretical computation. So for specification, NACP, National Structural Code of the Philippines, rho minus rho prime must be greater or equal to rho BD, balance design, but less than or equal to rho maximum. This is for the specification. And for the alternate or the theoretical computation, Fs must be greater than or equal Fy, F prime is greater than or equal Fy. These are the conditions. If this condition met by computation, the section is tension failure. Okay, this is the formula. Rho minus rho prime is equal to A is the total cross-sectional area of the bottom bar, this over BD, minus the total cross-sectional area of the top bar, compression bar, over BD. And this is also equal to this, AS minus A prime S over BD. Okay, we will going to substitute the values of this equation. AS is 4200, 42 squared millimeter. This is the number 30 bar have an cross-sectional area of 700, and this is 6 pieces. 6 times 700 is 4200. That's why we have this. Minus 1400, and this is the total area of the compression bar, this 2. 700 times 2 is 1400. and over BD, base, and deep. And this must be 0.018670. That's the value of the rho minus rho prime. Okay. Next is the rho BD. And this is the equation. 0.85 A prime C beta sub 1 D prime over Fy D times this quantity 600 over 600 minus Fy. And we have the value of this. 0.85 FC is 21. Beta sub 1 is 0.85 since the F prime C is less than 30 megapascal. So we use 0.85. And D prime is 70. This is this one, 70. Over the Fy 276, D 500, and this quantity 600 over 600 minus the value of the Fy, this one. And this must be 0.01425 to 20. So this is the value of the rho BD. And this BD is less than this one. Less than the value of rho minus rho prime. And that is okay. Okay, next to compute is the value of rho maximum, which is 0.75 rho balance. So the rho balance, this is the formula. 0.85 A prime C beta sub 1 over Fy times this quantity 600 divided by 600 plus Fy. Okay, substituting all the values, this FC is 21, beta sub 1 is 0.85 since the value of A prime C is less than 30 megapascal. And this is over Fy 276 times this quantity 600 over 600 plus 276. And this must be 0.037653, the value of the rho balance. And that's the time to compute the rho maximum. The rho maximum is 0.75 times the value of this one, and will give us 0.02823975. And therefore the value of the rho minus rho prime is greater than the value of rho BD, meaning this is the minimum, greater than the value of BD, but less than the value of the rho maximum. So this is okay. The section is tension failure according to the specification. Okay, we will check again using the theoretical computation. As we know, the A prime S is equal to 600 D times this quantity, C D D prime, C minus D prime over C. And from the previous video, we have this. Actually, this from C1 equals T1. So we have this equation to solve the value of A. Okay. And this also equals to AS minus A prime S Fy divided by 0.85 A prime C B. Okay. And we have the value of this. So 4200, as we computed from the previous slide, minus 1400 times this Fy and divided by 0.85 A prime CBD B, this one, and will give us the value of A is 144.3140 millimeter. This is the formula of that. But A is equal to beta sub 1 C. So therefore, C is A over beta sub 1. A now is 144.3140 divided by beta sub 1.85. The C is 170.0 millimeter. So that's the time we will compute the value of the F prime S, which is equal 600 times this quantity. We will go into substitute the value of 170 here for the C, and D prime is the 70, and it will give us 353.0 megapascal, which is greater than Fy. Okay, that is okay. For the Fs, this is the equation. 600 times this quantity, D minus C over C, and substituting the value of C here, and the D here is 500, we have 1164.20 megapascal, which is also greater than Fy. Therefore, the section is tension failure. Both the specification method of computation and as well as the theoretical method of computation. So, the section is tension failure. Okay, so this is the time to calculate the moment capacity of the section. Ultimate moment capacity. We have this the value 144.3140 millimeter, and the MU1 ultimate moment 1 is equal to this formula. Actually, this formula is derived from the stress block diagram, summation of moment at about T1 will give us this one. Okay, and we have the value of this 0.90. Okay, 0.90, this is moment 0.90 times the value of that 21. A is 144.314 times the B is 300, and times this quantity 500 minus the 1/2 of the value of A, then times 10 to the negative 6 to convert the unit into kilonewton meter. So will give us 297.5340 kilonewton meter. That is the moment capacity 1 of the section. Okay. Okay, the moment capacity, the ultimate moment capacity 2 is, this is the equation. Okay. This equation actually is derived also from the steel to steel component of the section. When we going to sum up the moment at about C2, this will come out. Or this equation is also the same with these two. This summation of moment at about T2, this will be come out. So either of this equation will give us the correct moment 2 of the section. So we will substitute 0.90. This is the cross-sectional area of the compression bar, 1400 times Fy times D minus D prime. This 500 minus 70 times 10 to the negative 6 to convert the unit. So will give us 149.540 kilonewton meter. And this is the moment 2 capacity of the section. So we have two moment there, moment 1 and moment 2. Those are an ultimate moment. So combining that, mu capacity is equal to mu1 plus mu2. So mu1 is 447. Where is that? 447. Oh, no. Yes, mu1 plus mu2. This is the mu1 and this is the mu2. So combining those moment, we have the sum of 447.1110 kilonewton meter. That is the capacity of the section. Okay. Now we will compute the moment applied, the ultimate moment applied. The ultimate moment applied is equal to 1.40 times the moment carried by imposed to the section plus 1.7 times the moment, live load moment. This is the dead load moment and the live load moment. And computing that, and the sum is 488.0 kilonewton meter, which is greater than the mu capacity of the section. So therefore, since the moment imposed into the section is greater than the capacity of the section, meaning the section is not adequate. So the section is unsafe. Failure. Okay. So that is the end of the computation for the USD sample problem. And maybe next video we will go into solve another sample for USD problem under the doubly reinforced USD method. So thank you for watching. Have a nice evening.